Welcome back to the FE exam review series, where we focus on problems built around fundamentals that will help you pass your FE exam. Today's problem is based on section A in the thermodynamics subject. I highly recommend you try the problem first before you watch the video solution, and you can do that using the first link in the description below. Let's get right into the solution. For each of the thermodynamic states defined above, what is the phase description of each case? We're given three cases above with some properties, and we're asked to determine is it a compressed liquid, a saturated mixture, or a superheated vapor. Now, the first thing I'm going to mention is that in terms of saving time, which you're always trying to do on the FE exam, if we are if we observe our choices here, looking at case one, for instance, most of the choices are unique for case one. If we go ahead and conclude that case one was a superheated vapor, we could immediately pick choice A and we'd have the correct answer. Now, the worst case is that it's a saturated mixture, and that would mean that we'd narrow it down to two choices, in which case we could just move on to case two and then we'd have our answer. So at most, we'd have to do two cases here. We don't really have to do three cases using that process of elimination. For educational purposes, we're going to go through all of the cases here. So let's go through. Now, what's important about this problem is understanding fundamentally the idea of the state postulate. Now, the state postulate says that if you're given two independent intensive properties, then you fully define a thermodynamic state, like given temperature and specific volume. What you could do is find enthalpies, you can find internal energies, you can find entropies. Intensive just means independent of the mass. You can see that these properties have a per unit mass if they're specific properties, and temperatures and pressures are also intensive properties. Independence is important, and we'll discuss it more when we're looking at case two. Okay, so usually to identify the state, what I like to do is draw a property diagram, and it's a good visual way to kind of identify the state. You draw a temperature, and because we're given specific volume in this case, I'm going to put specific volume on the x-axis. I'm going to draw my saturation dome, and at a given temperature of 180 degrees C, there's only one saturation pressure, which is Psat. Okay, so now that we have the general form of our property diagram, what we're going to do is, since we're given specific volume, we're going to compare our given specific volume to the specific volumes at these extremities here, where at the left side of the dome we have VF, which is the specific volume of a saturated liquid, and on the right side of the dome we have VG, which is the specific volume of a saturated vapor. Now, depending on where we are with our given specific volume, we could be inside of the dome, which would conclude that we're a saturated mixture. If we're greater than VG, we'd have a superheated vapor. And if we're less than VF, we have a compressed liquid. Okay, so what we're going to do is at 180 degrees C, see what VF and VG is in our property tables. So in the FE exam reference, in the thermodynamics section, in the steam table section, what we're going to do here is we're going to look at 180 degrees Celsius. And what we could see is that VF at 180 degrees Celsius is 1.127 times 10 to the minus 3. VG is 0.194. So we have VF is 1.127 times 10 to the minus 3. VG is 0.194. That's cubic meters per kilogram. And our given specific volume, the V1, is 1.25 times 10 to the minus 3. Now, our V1 is between VF and VG. That 1.25 is a little bit bigger than the VF value that we're given. What that means is that if we draw our V1, we'd have intersection within the dome. And if we draw that intersection point, it would be here. So because we intersect within our saturation dome, we have a saturated mixture. So the first one is a saturated mixture. Now what that means is that we could immediately eliminate choice A and we could eliminate choice D as well. We know we're either choice B or C. Let's move on to case 2 so that we could fix our choice. Now for case 2, we're given a temperature and a pressure. If we draw our property diagram here, I always put temperature on the y-axis because it's the least amount of things to remember in terms of uh, our direction of lines of constant pressures. Now for lines of constant pressures, I know they slope upwards. If we have like a PV diagram, for instance, you additionally have to remember that lines of constant temperature are actually backwards. They slope downwards. I usually stick to one of these diagrams so that I only have to remember one of them. And it's usually that temperature diagram. So at 150 degrees C, which is our temperature that we're given, we will have a saturation pressure. And we have a given pressure, P2, that we're not sure how it compares to the saturation pressure. So that's the information that we need in order to fix our thermodynamic state. Uh, if we go at 115 degrees C, what I'm seeing is that the pressure is 0.169 MPa or approximately 170 kPa. Psat is 170 kPa. And our given pressure, if we draw our line of constant pressure, which increases in this kind of direction, our P2 value is 175 kPa. We kind of picture that intersection where it's going to occur. The intersection will occur here in our compressed liquid region. Okay, so this is a very good visual way to really understand what your state is. We see we're a compressed liquid here. If we go up to our choices, what that means is that we're definitely going to pick choice B. That's the correct answer. Before we solve the rest of the problem, if you're enjoying this video and you're learning something, consider leaving a like and subscribing for more content like this. Additionally, if you're prepping for the FE Mechanical exam and looking for a resource that will help you pass, consider checking out my software, FE Interactive. It's the third link in the description below, and it'll give you access to multiple different sections, practice exams, review and improve sections, as well as a tips and tricks section, which helps you use your calculator better and save time on test day. An analytics page, which ties all of the different pages together. You get data for each of those pages where you can view, for instance, how you did on each exam, as well as a detailed solution manual for each exam so you know exactly where you're making the mistakes, what exactly is the misunderstanding coming from, and all of those are tied together with an overall data point. The overall data point can be reorganized in terms of performance so that you know what are my top 3 subjects, what are my bottom 3 subjects. Having this kind of data is super valuable since it helps you isolate your weaker points and fortify your strong ones. I'm confident that my software, FE Interactive, will help you pass the FE Mechanical exam. And again, you can check it out using the third link in the description below. You get 2 months of access for $29.99. Let's get back into the video. Okay, in terms of understanding the idea of independent, which I said we're going to discuss further in case 2, if you're given a temperature and a pressure, they're not always independent. For instance, if you're told that you are a saturated mixture and you're given a temperature, a saturation temperature, that means there's only one pressure you can be at within the dome. And for that given pressure, there's many different places where you could identify that property to satisfy the temperature and saturation pressure. So we're not fully fixed if we're within the saturation dome. We need another intensive property like specific volume. We need an enthalpy. We need a quality, which is the percent of the mixture, which is vapor. So that's an important idea to understand that if you're a saturated mixture, temperature and pressure are not independent. Okay, let's move on to case 3. Now for case 3, we're given a pressure, P3, which is 200 kPa. And we're also given an enthalpy, which is 2,800 kilojoules per kilogram. Now, again, what we're going to do here is draw our property diagram. We're going to go with a temperature versus enthalpy diagram here because we're given that enthalpy. Draw our saturation dome and draw our saturation pressure line, our PSAT, which we're going to assume is 200 kPa. Now we're not sure what TSAT is, but we can go ahead into our property diagram, into our property tables, and find out what that is. And our general strategy here is to compare this enthalpy that we're given to an HF and an HG value at our given saturation pressure. So if we go ahead into our property tables again, what I'm seeing is that at a pressure equal to 200 kPa, which is somewhere between these two pressures of 198 and 232, I'd have some enthalpy properties which I could extract and compare to my enthalpy that I was given. I'm going to screenshot this table here. That's this stuff right here. And we're going to paste it down here. Okay, so I know that for my given pressure, which is 200 kPa, I'm somewhere between these values. If I wanted to do this problem completely, what I do is I'd interpolate between the HF and HG values. This is the H column here, HF, and this is HG. I'd interpolate between these values here at that given pressure. But what I know is that 200 kPa is much closer to 198 kPa compared to 232 kPa. So I'm going to assume my HF is around 504 and my HG is around 2707. And what my H that I'm given is, my H3 is 2800 kilojoules per kilogram. And I can see that that's greater than my HG value. Even if we weren't completely accurate in our interpolation, the most that HG could be is this 2713 value. So I definitely know that for sure I am above that H value. I'm greater than HG. So this is my H3 here. And I'd have intersection to the right of the saturation dome, which is the superheated vapor region. Choice B. If we quickly view the explanation to kind of go over what we've been working on, we discussed the idea of property diagrams in the state postulate. For the first case, we compared our specific volume to that of a saturated liquid and a saturated vapor, and we saw that we're within the saturation dome based on our VF and VG value. Since our given V is within those values, we know that we're a saturated mixture. For case 2, what we did was compare our pressure to the saturation pressure. And what we saw was that our pressure was greater than the saturation pressure, meaning that we are a compressed liquid. We intersected on the left part of that saturation dome. And for case 3, we used that idea of approximate interpolation, where we saw that our given H value was greater than the HG value, corresponding to a saturation pressure of 200 kPa. What that means is that we're a superheated vapor. We intersect at that kind of right portion of the dome here. And we concluded that it's choice B. If you enjoyed the video, you learned something, please leave a like and subscribe. Thanks for watching. I'll see you in the next video. Goodbye.